In this video I'm going to talk to you about solving indicial equations without a calculator. So really what we're looking for is ways in which we can equate the bases or have the bases the same so we can then equate the powers. So what I'm going to do is just look at, well, if you've got the same base, so base here, this is the power, then surely if the bases are the same, then we can say that therefore m equals n. Now I'm going to apply this basic rule to some non-calculator examples of some indicial equations. So start with a real basic one. Let's suppose I needed to solve 3 to the power x equals 81. Well, we know that 81 can be written as a base of 3. So we can change its base to make it a power of 3. So 3 to the x is the same as 3 to the power 4. 3 to the power 4, of course, is 81. So now, therefore, we can say, well, therefore, x must equal 4. Let's look at a little bit more of a trickier one. Let's put some algebra in there. Well, let's suppose I had 4 to the power x minus 1 equals 16. Again, we know that 16 can be written as a base of 4. So I can say 4 to the power x minus 1 equals 4 to the power 4. Now the bases are the same, I can now equate the powers and say, well, x minus 1 equals 4. Solving this equation by adding 1 to each side tells me that x must equal 5. And you can check that. 5 take away 1 is 4. 4 to the power 4 is indeed 16. Let me clear some space. Again, this one's no different really, because if we look here, we've just got 36 that can be written as a base of 6. So because I'm dealing with in some algebraic expressions as the power, I've got to use my laws of indices here. So I've got, I've written 6 to the power 6, supposed to be 6 squared. Hold on a second. 6 squared to the power 2x minus 3. Now obviously I've got a power raised by another power here, so I do need to do my multiplying. So before I can equate the powers, I need to make sure I've got this correct. So it's 6 to the 2 times 2 is 4x minus 2 times 3 is 6. Now the bases are the same, I can now equate the powers and then go on and solve the equation. So I'm dealing with x's on both sides. So what I'm going to do is subtract some x's and add the 6's, leaving me with 5 on the left-hand side by the time I've added the 6, equals, subtract the 3x from there, leaves me with x. So 5 equals x. Now I can verify this because I can sub x back in. 3 times 5 is 15. 15 minus the 1 is 14. So that's 6 to the power 14 there. And on this side, 2 times 5 is 10. 10 minus 3. Oh, hang on, I need to do it on this one, don't I? Because, of course, it's a different base. 4 times 5 is 20. 20 minus 6 is 14. So I've got 6 to the power 14 equals 6 to the power 14. So we've verified it. Now let me have a look at what happens where we've got some numbers multiplying, because you do need to make sure that if you're going to use your laws of indices, the bases are the same. So let's use this one. 2 to the power 3n multiplied by 16n plus 1 equals 32. Now looking at this example, we can see here that 16 can be written and 32 with bases of 2. So if I rewrite 16 as a base of 2, 16 is 2 to the power 4. And obviously the power is n plus 1. And 32 can be written as 2 to the power 5. Now, let's work this out by raising the power of a power. So I've got 2 to the power 3n multiplied by 2 to the power 4n plus 4 equals 2 to the power 5. Now I'm in a position now where I can simplify the left-hand side. Because the bases are the same and there's a multiplication sign, I can add the powers together. So I've got 3n plus 4n gives me 7n. So 2 to the power 7n plus 4 equals 2 to the power 5. Now that's left me with the same base. I can now equate the powers. So we can say that 7n plus 4 equals 5. Solving that, subtract 4 from 5. Leaves me with 1, so 7n equals 1, so n must equal 1/7. Squeeze that in at the bottom there. Alright, I might just do one more example. I'll clear some space. Okay, so what we see here is quite a difficult indicial equation to solve. When you look at this, when you see something that's got equal to 0, and within this we've got some bases of 5, we can think quadratic expression. Now if I then make this 5x as a substitution, if I say, well, let's pull out, I can show you that there's a 5x in each of these. Because of the raising a power of a power law, what you've got is 5x multiplied by 2, which is the same as squared. Right, so there's a 5x minus 4 bracket 5x minus 5, which is technically no x value. If you substitute 5x equals, say, y, another variable, you've got y squared minus 4y minus 5 equals 0. So straight away you think, right, it's a quadratic, I need to solve that. We can solve it because it's equal to 0. So the first thing we say is, well, does it factorise? And in this case, it does factorise. It factorises quite nicely. We've got minus 5 and positive 1. So we go y minus 5 and y plus 1 equals 0. Now solving using the null factor law, y equals positive 5 or y equals negative 1. And we have two solutions to this particular equation. And don't forget that y equals 5 to the power x. So let's solve those individually. So let's look at the first one. 5 to the power x equals 5 to the power 1, doesn't it? So therefore x equals 1. And looking at this one, y equals minus 1. Well, this one has no solution because we can't put this to a power, which is going to give us a base of 5. So this one has no solutions. And that's pretty much everything you need to know about indicial equations.